the thing that I'm going to go ahead and push out there under Twitter. Remember on my syllabus I said there, yeah. So if you want to go back and listen to it, you can. So one of the things, astronomy is not equal to astrology. What's astrology?
Like your horoscope?
Like your horoscope, exactly. And we talked Wednesday that I'm the sun now, and my fist is the earth. As the earth goes around the sun, we get to see different stars. So we see different stars over here as we do over here. So that's kind of how the astrology came in. Depending upon the month you were born, you see a different set of stars, and I'm not sure. Reagan believed in it, but anyway. So this isn't astrology, but anyway. I hope you find it a very kind of pleasant science. I think it helps. It's humbling for me. Astronomy is humbling. So you might kind of pick that up a little bit. Cool. So how do you do well in this class? Well, even though I don't give a reading assignment, I would go ahead and read your textbook. Okay, I think it's good. Pay attention. I kind of mentioned that before. That's why I kind of took some words out, so you got to fill in the words here and there. Make sure that on Fridays, you're going to need to turn in assignments. Hi. There's no assignment due today, but there is an assignment due on the 20th. Okay, so remember I gave you that sheet? And actually, I think it's just chapter 1. You can turn in assignments early, but you can't turn them in late. And make sure you get to at least 4 labs. And I'll try to remind you about the labs as they come up. But like I said about last night, thinking about y'all can do those do on your own labs anytime. So the weather's not going to cooperate, I don't think, this weekend. So if this is meteorology, you could get some good pictures of weather, but no. All right. So a little bit about me. My background is in chemistry, and actually you might kind of see those little atoms up there. Right after this class, I have my general chemistry 2 class, so every once in a while I'll bring toys for them. But astronomy, and actually we're going to talk a little bit about this today, that astronomy and chemistry, there's definitely a link. Okay, because in chemistry we talk about the elements. We talk about hydrogen and helium and carbon in chemistry. And actually, I'm going to try to convince you, but the carbon and the hydrogen, the helium, the silver, the uranium, that actually came from stars doing different things. Okay, so I just think that is so cool. All right, so that's my background. So I'm going to we'll try dimming the lights here, see if we like this. All right. So at first blush, that might look like, oh, there's some stars there, okay? But if you look a little bit closer, those stars look a little fuzzy, okay? And honestly, those little patches of light are not stars, those are galaxies. I have a slide coming up that says we think that there's about 100 billion galaxies in the universe. But as of, gosh, was it summer or fall? Oh, wait, we're spring. Anyway, as of the last year, they have doubled that to 200 billion galaxies. I know, my gosh, that's a lot. And if you're kind of familiar with the whole galaxy thing, each galaxy is made up of a bunch of stars, like 100 billion stars in a galaxy. So you can do the math and think there's a lot of stars. So this is, I think, if this is the one I'm thinking of, this was taken by the Hubble Space Telescope. I don't know if you're familiar with that, but I'm going to make my fist the Earth now. This is the Earth, and the Hubble Space Telescope actually goes from pole to pole in about 90 minutes. Okay, so it's orbiting the Earth, I know. And when we meet for lab on an evening, if you know the timing, you can look on the website and stuff, and sometimes you can actually see the Hubble Space Telescope passing over. It is very cool. It doesn't look like the Hubble Space Telescope, but you can see the light. I know, it's so cool. You wave and everything in the Hubble Space Telescope. Okay, but anyway, this was taken by the Hubble Space Telescope kind of early on in its mission, and what it did was, have you heard of the Big Dipper? Yeah, okay. What it did was, near the Big Dipper, kind of the handle of the Big Dipper, it looked where there was no stars. And it said, okay, Hubble, you're so cool. Tell me what's out there. And this is what they saw. Can you imagine the first scientist to see this image? Oh my gosh. So anyway, I think that is so cool. So we're going to build up to galaxies, but what do you think this is?
Earth.
This is the Earth, yeah. This is our planet. And our planet is not alone. Okay, what do you think that yellow thing there is in the center? That's the sun, yeah. The sun is just a star. It's kind of like Goldilocks and Three Bears. It's like a middle star. It's kind of like in the spectrum of stars. It's kind of nice. You kind of see the planets orbiting. We are on the planet Earth, and we'll be talking a little bit about how special our planet is. Okay, well, what is this, you think, then? A galaxy, exactly. Anybody know which galaxy we're a member of? The Milky Way. Yes, I love Milky Ways, too. Dark Milky Ways are the best. Yeah. And we're actually about halfway. Actually, most galaxies, including ours, has a black hole in the center. We'll be talking more about that later. So there's a black hole there, kind of the edge of the galaxy. Galaxies are kind of nice and flat because of how they've been rotating over the hundreds of thousands of years. So they're kind of like a frisbee. So we're halfway between there and the edge. Okay. And this is to try to kind of show you now we have another galaxy shown in the same figure as our galaxy. Okay. So what we see in the universe is that galaxies are kind of organized, okay, into what we call groups, and groups are organized into clusters. Okay. So those are kind of just a glimpse. That figure is trying to show you kind of the smattering of galaxies. Now, your textbook, if you're into such things, such detail, be careful when you look at a photo. Is it a photo or a figure? In your textbook, it will tell you. Okay. One of the things about astronomy is when we look out at stars or galaxies, we can kind of tweak what it looks like, the photo, if we look at it in a different set of eyes, a different wavelength, what we say. So sometimes they're in different wavelengths too. Okay. So let's talk distances for a minute. How far is it to get to yonder? Well, two important distances in astronomy. One is an astronomical unit, capital A, capital U. An astronomical unit is the average distance. Now I'm going to make myself the Earth. At 1 AU is the average distance between the Earth and the Sun. One of the things that Kepler back in the 1600s found out was that actually this distance varies a little bit. Okay, sometimes we're at what we call perihelion, and sometimes we're at what we call aphelion. So it does vary a little bit as the Earth orbits the Sun. So 1 AU. The other one is a light year. Okay, now to describe a light year, if I go over here and I turn off the light, and I'm going to turn on the light here in a minute, we think all at once. I just think everything's amazing. Like, who figured out how to make electricity go to that light bulb? I know. Like, it is crazy. So I close the circuit, electricity flies through those light bulbs, okay, and it excites the gases that are in the light bulbs, and then all at once, basically, it starts to shine, okay? But we think it happens just like that, okay? But it takes the light a certain amount of time to get to me. So it doesn't happen just like this. So if we were to take this light, I don't know how we would do it, but we were to take it and put it at farther, so I'm on the Earth, farther than the Sun, because that's 1 AU. If we were to put this a distance called 1 light year away, okay, and somehow I was able to turn off the light, it would take a year before I would see that light turn off. It's nice. I know. Because it takes light a certain amount of time to get from point A to point B. Okay, so that's how we do a light year. Okay. The closest star to us is, I believe, 3 or 4 light years away. Okay, so that's so cool. So if that star, like say it's 4 light years away from us, if that star suddenly ceased to exist, it would take 4 years for us to know that it wasn't there anymore, a light year. I know, it is so cool. Okay, so distances. So here, I believe to me, and I'd have to double check, this kind of looks like a photo-ish, right? And this is a figure, okay? So this is I mentioned the closest star to us. This is the closest galaxy of stars to us. So this is the Andromeda Galaxy. And the Andromeda Galaxy has a couple of companion galaxies. I believe this is one, and I don't know if there's one hiding there. But it's pretty big. And not to scare anybody, but you probably have heard this, that the Andromeda Galaxy is actually getting ever closer to the Milky Way galaxy. Okay? Yeah, I know. So I've seen documentaries, and maybe you have too. At one point, they are actually, and galaxies do this, they're actually going to merge. Okay? They might have enough momentum to kind of get together and then kind of scoot out. Maybe they're, okay? But I think what I've heard is probably their black holes will combine and they'll form one big galaxy. Isn't that cool? I know. So right now, the Andromeda Galaxy is far enough away. You can kind of get a sense for where it is in the sky. This is the constellation Pegasus. It has what we call a great square Pegasus. And if you find the square, you're in good shape to kind of hop to, we do a lot of hopping in astronomy, to hop to the object, the Andromeda Galaxy. So anyway, the Andromeda Galaxy is 2.5 million light years from us, and it's the closest one. You can actually see it with your naked eye. I mean, it's just fuzz. Binoculars are better. Okay, so 2.5 million light years away. So it takes light 2.5 million years to get to us, traveling at 186,000 miles per second. That's how fast light travels. So,
Okay,
yes?
so does that mean it could just not exist right now and we wouldn't know about it?
Right.
So trippy.
She asked, I know it is very trippy. She's like, could it not exist and we wouldn't know about it? Yes. And we'll talk more about that later, but there's this kind of thing called look-back time. So astronomers, I don't know, to me look-back time is almost like we just kind of have to pretend it is as we see it, in a sense. Yeah. But kind of related to that, one of the things that astronomers are always looking for are these supernova events, like a blow-up star, supernova. And even though galaxies are way far away, supernovas are so energetic that they can actually see that light. Yes, exactly. And so they're kind of searching for those. So I just think that's okay. I am humbled, like I said. So now I told you this is not a math class, and it's not a math class, but I want you to kind of know a little bit about scientific notation so you get a sense if you see a number that is in what we call scientific notation. It's just a way to write a number. The good candidates for being a number to pack up this way are the big ones. Here's a big one. Well, let's see. Is that 12,300,000,000,000,000,000? Something like that, kilometers. You're like, oh my gosh, all those zeros make me go batty, okay? And then that little one, okay? So here's my instructions in case you ever need to. But this is kind of how we pack them up. Basically, you find where the decimal is, and I'll kind of cheat with these examples. Where is the decimal in this number?
At the very end.
At the very end, perfect. So I'm going to kind of put a decimal there. Okay, I'll draw a circle around it. And of course, the decimal's here, there. Okay. So first off, you find the decimal, and you move it so you get a number that's between 1 and 10. Okay, so in this case, I would move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I would move it 10 places. Okay, so that's why it would be 1.23 times 10 raised to the 10th power, because I had to move it 10 places. So. Bottom line is, if you see in astronomy something that has 10 raised to a power, think of basically that power kind of tells you how many zeros you got to go. And then this little one, we don't do as much of that in astronomy, but for this small number, I go 1, 2, 3, 4, 5, 6, 7, 8, 9. I go 9 places over, okay? And so what, that's going to be 4.721 times 10 raised to the negative 9th, since it's a small number. I get my left and rights mixed up, so I don't emphasize left and right. Okay. So I think I have on the next page some examples. No, I think you're okay with this. All right. This slide you don't have either, but let's just check it out a little bit. And this, we're going to be building up to the whole that star being like 4 light years away, and we're seeing light from that star as it was 4 years ago. We're kind of building up to that. So if you're going 60 miles in 1 hour, okay, 60 miles per hour, if somebody says you go 30 minutes from your destination, how many miles are you from your destination?
30.
Yep, I'm liking 30 miles. Perfect. I'll put it 30 there. 30 miles. So basically, we are taking time and converting it just in our brain to distance. We're 30 minutes away. We're really 30 miles away if we're going 60 miles per hour. Well, what if we take our speed and we jack it up times a factor of 10? So now instead of 30 miles, we're 300 miles away. Yep. Very good. So let's go ahead and take our original one. Instead of going 60 miles per hour, we're going to jack it up 1, 2, 3, 4, 5. A factor of 10 to the 5th. So basically, we're going 30, 1, 2, 3, 4, 5. Okay. If you were traveling at, oh my gosh, 6 million miles per hour, and I say I'm just 30 minutes away, then you must be, what, 3 million miles away, traveling at that speed. Now this down here, well, don't worry about that down there. Now you do have this light. Okay. So light travels about 186,000 miles per second. In the metric system, that's kind of a nice 300,000 kilometers per second. So from the moon, it takes 1 second for light to get here. If we were to go ahead and take into consideration how fast light travels, that makes the moon a distance of about 300 kilometers. Okay, so 1 light second is 300 kilometers. So we have like if the moon should cease to be, we have a second delay before we know it's no longer there. The sun is farther from the moon, so it takes light 8 minutes to get from the sun to us. So you might have heard this in some documentaries. They're like, yeah, if the sun should cease to be, actually the way it interacts with the fabric of space and time and even the little energy it's sending us, there's going to be an 8-minute delay. So you got 8 minutes. So considering how fast light travels, that puts the sun at an average distance in kilometers of about 1.4 times 10 to the 8th kilometers. See, this is where I was hoping you kind of know a little bit about scientific notation. That 10 to the 8th means you take that decimal place and move it over 8 places. So that's a lot of kilometers. Now, Sirius is not the closest star. Proxima Centauri is the Alpha Centauri? I guess Alpha, not Proxima. Proxima Centauri must have been in that movie with the blue aliens. Anyway. Sirius is a bright star in the nighttime sky. Sirius is called the dog star because it's in the constellation Canis Minor. So anyway, it's the brightest star, and it is 8 light years away. So considering how long it takes for light to travel, how quickly it travels, that puts Sirius at a distance of 7.6 times 10 to the 13th kilometers. So, 13 places move the decimal, and there you go. Thank goodness for scientific notation. And we already said how far away is the Andromeda Galaxy. Well, in terms of traveling at the speed of light, it's 2.5 million light years away. And that puts it at a distance of 2.4 times 10 to 19th kilometers. So I hope you can see this. See how this bullet up here, it kind of got my face slide. So it's like we talked about. When we see an object, that object is no longer look like that. Okay? It looks like something else, but we can't see what it looks like because it takes light a certain amount of time to get to us. So we're seeing it as it was in the past. The further away we look in distance, the further back we look in time. You have one of those? Yeah. Okay, good. Hope you don't mind, I'm kind of looking at it. Okay, thanks. Okay, yep, so we're looking at old light. Just old light. So sometimes, like when I'm looking through the telescope, I'm like, I feel so lucky to get that energy in my eyes, thinking of how long it took that energy to get to me. And then it's spent. It's like it's in here, and there it goes. Okay. So the term cosmology, now we aren't going to get to cosmology until like Unit 5 in here, but cosmology basically deals with, well, how is the universe structured now? And we talked a little bit about that a minute ago. Well, we have galaxies that are kind of clustered together, and those galaxies actually kind of are hanging out on these little void regions, which is kind of neat. That's cosmology. The Big Bang is cosmology, the origin of our universe. So that is still evolving. There's new science being found out to kind of tweak the Big Bang theory. Have you ever watched the Big Bang? Yeah, okay, the television show. There's still evidence coming out to kind of tweak that, but bottom line is they think that our universe was initiated all at one time. So there was a definite beginning, and so that kind of puts an edge to the universe. Now there's an edge to the universe, and then there's an edge to our observable universe. So that's kind of a difference. Okay. So what we have here, and if you come out to the Whitty Observatory there by Sperry, north of Burlington, we've got actually 2 of these. These are domes, okay? And I just think domes are cool. I'm just easily impressed. So what happens is there's a telescope in there, okay? And then actually, it looks like a silo, right? But this round part actually swivels around. There's a slit in one place, and it swivels around to see what sort of the part of the sky you want to see. Okay, now, observatories like this, domes, I guess I should say domes, they're not heated. So, yeah, I know, so it's kind of cold right now. They're not heated because what heat does is it kind of messes with your optics. Heat gives you like swirlies that you don't want to see when you're trying to get the light from something. But that's not my point here. My point is, here we have 2 galaxies. We have kind of this nicely defined galaxy right here. You're probably kind of familiar with, a lot of times galaxies have these awesome spiral arms, okay? And then we have this kind of fuzzy looking galaxy over here. So I'm going to call the first one A and the second one B, and then I'm going to ask you a question. This one's A, okay, and this one's B. So the question goes something like this, A or B, and I'm going to ask you for a show of hands. Which one will the light look, I know. Which one will look younger? It looks younger. Okay, so one's going to look older, one's going to look younger. Okay, how many people think, so what did I say, younger? Which one is going to look younger? How many people think that by the time the light gets to us? How many people think that A will look younger? Okay. How many people think that B will look younger? Okay, so somebody who said B, why would B look younger?
It's just starting.
It's just starting.
It hasn't had time to make that shape.
Yeah, okay, you're going by the shape, and he's right. He's right. He's saying, very good. He's saying this one looks all kind of smeared out, and actually galaxies go through a process of becoming defined or refined. And you're right, that one's a baby. You're right. What's another way of thinking that it will look younger?
The light of it takes longer to get
Yeah.
to us, so we're seeing a later image. Or
Yep.
earlier image.
She said the light took this long to get to us, okay? So there's more of a delay. So that delay actually means that we're going to see more of a baby picture of that one. So it will look younger. Yeah. Good job. So this guy will be younger. Awesome. Okay. Oh, wait. One back. So one of the things, the overall objectives of this semester, these 16 weeks, is I'm going to throw some dates at you. And one of the dates is actually listed here. So we've got basically the edge of what we can see as basically kind of the beginning of there's no galaxies, there's no stars, that distance is about 14 billion light years away. I have to think about this. So that we're looking at, as far as we can look, was created about 14 billion years ago, because it's 14 billion light years away. Okay, so that's one of the things that kind of gives the timing on how old our universe is. It hurts my brain, honestly. But I think it's so cool. And we call that our cosmological horizon. Okay. So, on a given night, if we have a viewing, when I get the telescopes out, or if you go to the observatory, they'll put something in the telescope, and sometimes they will say it's a Messier object. They'll say it's Messier object. And they won't say it's Messier object number blah, blah, blah. They'll just say it's M number blah, blah, blah. Okay? So Messier, back in the 1771, actually, he was, I'm not sure, I'm thinking he was a professor. Okay? And as sometimes professors at big universities do, he had kind of like a following. Okay? So he had a bunch of students working for him. I don't know if they paid him or not, or paid the students. Okay? But Professor Messier wanted to find comets, and we'll talk more about comets. Comets are cool, and there's a few out right now, so we'll see if we can find them on a viewing session. But comets actually, if these fingers are stars, say these fingers are the Big Dipper, okay? A comet will kind of appear to be here one night, and here the next night, and here the next night. You kind of see how I'm moving. Okay, so a comet will move across the nighttime sky, but very slowly. Okay, and what comets are is basically they're an icy, chunky thing that came from most likely out beyond Neptune. Okay, so it kind of came out and it got close to the sun and it started fizzing. That's it. And so we kind of see basically the sun kind of lighting up the fizzy part. That's a comet. So he was looking for these, and he saw a bunch of fuzzy things that looked like they were comets, and they were so annoying. He's like, all right, students, find these fuzzy things and write them down so I don't mistake them for comets. Okay? So those fuzzy things are called our Messier objects that we know and love today. There's 110, 109 of them, and these are all kind of pictures of different Messier objects. Okay? So that's kind of where we call observational astronomy. If you're looking through a telescope, you're observing. That's kind of where observational astronomy kind of gets some of its things from. So you probably notice some of them have different shapes. Let's see, M31, I don't think I'm going to be able to find it. But we looked at the Andromeda Galaxy a minute ago. That's M31. Okay, and I noticed here that I made a note at some point in your textbook. Your textbook has great appendices. Not like the appendix, but has great appendices. What I started to say, I don't know how much I want to go into this, is I see galaxy, 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 galaxy. Okay, now, this is not a galaxy. Okay, that actually does it look like a star that's kind of blowing up? Yeah. It's kind of a star that's kind of letting go of its material. Very good. And so this is kind of, we call these nebula. Very good. So it's kind of an assortment of things, Messier objects. Okay. So leaving the whole universe thing, kind of coming back to our own little star, our whole neck of the woods, we're going to take a whole unit and talk about planets. Okay? And this is actually just to kind of put our whole solar system into perspective. I'm going to click on that Josh Worth link, and we'll see what you think. I was kind of surprised when I clicked on it today. I was like, really? That's how that works? Okay. And I actually, if you're keeping track of me on Twitter, just this morning I went ahead and took this link and put it on Twitter too. So the way this works is we're going to take a pixel is the size of the moon. I'm going to go over. Okay. So 1 pixel is the size of the moon. So you kind of get, there's 1 pixel, and it's the size of the moon. So there's a couple of different modes to view this. But if that's the moon, then relatively speaking, this is the size of the sun. And notice down here, it's saying how far away it's gone. 0.1 light years, minutes, excuse me, 0.2 light minutes. And I think this said if you want to go any faster, you'll have to talk to Einstein about it. So we're going very, 0.3 light minutes. What did we say? Earth is 8 light minutes? Okay, what's the first planet going to be? Mercury, yes. So I like this little animation because sometimes we think the planets are closer to the sun than they really are. .8 light minutes.
It puts into perspective why it took like 17 years to get to Pluto.
That's a good point. It puts into perspective. And those things are booking, you know. You must be a New Horizons fan too?
Yeah.
Yeah. And it was like a flyby, New Horizons, and it's an amazing engineering feat. And New Horizons has still gone out beyond Pluto and gathering data.
Wonder if it'll find Planet 9.
They're talking about Planet 9. See, this is like still trying to get to Mercury. Pretty empty out here. Are you serious? So if we're 8 light minutes, we're already about 2 light minutes. And I'm pretty sure this animation is the speed that it's traveling is to, or how much it's traveling is to scale with the speed of light. So I think that's kind of cool.
This is where Mercury was 2.5.
Oh, thank you. I was wondering when it was going to come up. So it should be, oh, here comes our first planet. Very good.
I was close.
Yeah, and it is to scale, so see how big it is compared to our little pixel. Sometimes observational astronomy, I tell people it's kind of like fishing, where you just kind of soak it in. We didn't miss it, did we?
It's gone.
There it is.
Oh, heavens. All right. So what's the next planet going to be? Venus. So you guys see these symbols up here? Okay, that's Mercury. Venus, that's the symbol for Venus. Is that not cool or what? Wait, is it, yeah, it is Venus. Okay. That's the symbol for Venus. Final answer. That's the sun, Mercury, Venus. Final answer. Here we go. We're right to Venus. Whew. I know. There we go. 6 light minutes away. Then what's after Venus? Earth. And there's the symbol for Earth. You Stargate people, you. There's the Earth and our moon. Okay, what's after the Earth? Mars. I wonder how far away Mars is. Okay, so it's about 13 light minutes. So Mars is a very busy place, in case you didn't already know this. Of the planets that are being explored, oh my gosh, Mars has rovers. It just blows. You can get almost, I think, real-time images of Mars rovers pictures. You're like, oh, how cool is that? So anyway, there's Mars. What comes after Mars? Jupiter.
Really far out.
It is. Okay, so about 13 light minutes. Yes, Jupiter skips. When we get out to the Jupiter, look how big it is too. So what are these little dots, you think, around Jupiter? They're moons, yep. Jupiter has like 100, I want to say, it's like 120, 164. I get Jupiter and Saturn mixed up, but a lot of moons, okay? Yep. Okay, Jupiter's the biggest planet. Jupiter then switches gears from the other planets because it's gaseous, okay? It's a gas giant. What comes after Jupiter? Saturn, symbol for Saturn. That's 43 light minutes away. Woo. Well, you guys already know this. Actually, we have sent spacecraft to study Jupiter too. So, and usually the gas giants, we're not only concerned about the planet, but we're also concerned or interested in its moons. Yep. Okay, so Saturn, well, let's take a quick look. Woo! Saturn, there's its biggest moon, Titan. And what's this around Saturn? The rings, yep. And then what comes after Saturn? I heard somebody say Uranus. Uranus, Uranus. What color is Uranus? Blue. It is blue. Kind of turquoise. I like turquoise. Okay, and it's, I don't know if you could tell, but it's smaller than Saturn. And then what's our last planet, official planet? Neptune. That looks like the Neptune thing. Very good. And so what's this a symbol for, you think? It is the symbol for Pluto. Let's take a look. So Neptune is 250 light minutes from the sun. And here's Pluto. Aw. See what it says underneath there? Yep. You can't. We still love you. So.
Why did they take it out?
Why did they take it out? It's kind of related to this 9th planet out here. Okay. So, and I remember, did I tell you that comets? Remember I told you comets are basically something out here that got nudged, and it orbits the sun and it kind of fizzes. Well, the thing is when they actually came up with a 10th planet. And that started the demotion of Pluto, basically. So out here, there's like stuff that never turned into a planet. And there's this big old thing out here called Eros, okay? And Eros is larger than Pluto, and it orbits the sun. But Eros, how do I say this? Eros isn't a planet either. And the criteria, they said, is the object that you want to be a planet needs to have, and this is where Pluto failed and Eros failed, needs to have no crumblies in its path as it orbits the sun. It needs to have cleared its path. Okay, if it's big enough to go ahead and basically gobble up all that stuff and make it part of itself, then it can be a planet. So that's where Pluto failed. So anyway, yeah, very good. What else do we, how close are we? Thank you for hearing. Well, I think this is a good place to stop. So we won't quite finish up part 1, but just things to think about. We'll kind of switch gears on Monday.
So we don't have daily homework?
Nope, homework's always going to be due on Fridays.